Okay, the sky this season. Now notice I've changed it from the sky this month to the sky this season. So June 11th to September the 10th. There's actually no events per se that I'm really going to talk about, but because we're not planning to have regular meetings in the summer, I just decided to go and do the whole season. Okay, so highlights. I'm just going to talk about some facts about the brightest summer stars, and of course, I'm going to talk about some facts about the summer solstice. So tonight, June the 11th, 10:30 p.m., you go outside, the sky is going to look a little bit like this. And if you just take a look straight up, that's where the zenith will be, straight above you. And then that's the familiar Big Dipper. So it's going to be practically right overhead. And if you arc to Arcturus, that will be Arcturus. That's the brightest star in the northern hemisphere. And then if you go over to here, again, very close to the zenith, you're going to find the summer triangle. The stars are Vega, Altair, and Deneb. Okay, so basically these are the stars that I want to just talk about because they're going to be up there. They're going to be easy to spot, even when it's, well, I think as Charles pointed out a little earlier on, these are the first stars to appear during the evening. And of course, with long evenings, you don't want to wait up too late. So you'll be able to see these stars. And let's just talk a little bit about some interesting facts about them. Here's a close-up of the summer triangle. And you see that it's in a fairly densely packed area of the sky. You can see the Milky Way in the background. So let's just take a look at Vega as our first star. So here's a shot of Vega, and it's the most studied star there is in the sky, except for the sun. It was the first star to be photographed way back in the 1800s. It was the first star to be spectrally analyzed. So it's been always had a very special place. It turns out that it's a reference star for brightness. And so it used to define what it meant to be zero magnitude. It's actually a little bit off that now, but it is a reference star. And it's also a reference star for color. There are three types of colors applied to stars, and in two of those colors, Vega is zero, color zero. So it's the reference point. It has a magnitude of 0.026. So if you're new, just you have to remember that it's a little bit like golf. The lower the score, the brighter you are. So think of 0th, first, second. You know, if you come first in the Olympic Games, that's good. Second's not so good. Okay, so again, 0 is even better than first. So we've got a magnitude of a 0.026, means it's a very, very bright star. It's 25 light years away, and its mass is about twice the mass of the sun. It's about 2.5 times the radius of the sun, so that means it's less dense on average. Its surface temperature is 9,600 Kelvin, which would mean that it's white with a bluish tinge. And I think looking at that picture, you can observe the definite bluish tinge to it. That makes its surface temperature about 1.66 times hotter than the surface temperature of the sun. So with the effect that it's larger than the sun and it's hotter than the sun, it turns out that it's 40 times brighter than the sun. And it's only 455 million years old, which is about 1/10 of the solar age, but it's expected to be about halfway through its life. So it's like the general principle of stars is the heavier you are, the brighter, the hotter, the bluer, and the faster you burn out. And certainly Vega is an example. It's going to burn out in about 1 billion years as opposed to this sun's 10 billion. So it's about halfway through its life. Now, it turns out that it's rapidly rotating. That means it rotates once every 12 and a half hours. And if you compare that to the sun, it goes around once every 25 days. So it's really hustling. It's going actually at 236 kilometers per second at the equator. So that's like, about 8 times faster than the sun is, or that the Earth is orbiting the sun. But this is around this star. So it's the centrifugal force, if you want to say it that way, is enormous. So here's a picture. I don't know if you can see the comparison of the sun because of my picture on the side, but there's Vega. Notice how it's an ellipsoid. It's quite a bit wider at the equator than it is from the North Pole to the South Pole. It turns out that if it was going 10% faster, that would cause it to fly apart. So it's actually kind of on the verge of flying apart. It's been recently discovered that there is a dust cloud around Vega, even though it's been problematic to find out if there is any planets. But there's a warm inner belt and a cool outer belt, and that would correspond to, in the case of the sun, the warm asteroid belt, and then the cool Kuiper belt, or Kuiper belt, which is much farther out, way beyond Neptune. Notice that if you draw the solar system to scale, it's a lot smaller than the system around Vega. So that's what you can sort of think about when you take a look at that bright star in the summer triangle, Vega. Now let's go on to Altair. Altair is down at the odd end, the long end of the triangle, and it is sort of second fiddle to Vega, but in many respects it's just like it. It's just not quite as great, shall we say. It's got a magnitude of 0.76. So it's not as bright. It's a little bit closer at 16.76 light years away. 1.8 solar masses, so it's getting up there. Notice the variation in temperature here. That's not error. We'll talk about that a little bit later. But it's 6,900 Kelvin to 8,500 Kelvin, which makes it about 1.2 to 1.5 times hotter than the sun. And it's 10.6 times brighter. So compare that to Vega, which is like 40 times brighter. This is 10.6 times brighter. But it has beat out Vega in one particular, and that is it's the first star to have its surface imaged, of course, with the exception of the sun. And so this is basically what the shape of Altair is, and you can see it's quite bloated. It's not a sphere at all, and that's because it's rapidly spinning, 286 kilometers per second at the equator. It's at 76% of breakup speed, and notice that the pole is tilted with respect to us, so we don't see it. We don't see it end on. We don't see it side on. It turned out that by studying this surface, this confirmed gravity brightening at the pole. What that basically means is that where it's spinning most rapidly at the equator, it's cooler, and where it's hardly spinning at all, or in fact not spinning at the pole, that's where it is hottest. And that's why you get this range of temperatures, 6,800 to 8,500. There's that much variation in temperature of Altair just by whether you're looking at the equator or whether you're looking at the pole. So that's Altair. So let's go on to Deneb. That's the third of the stars of the triangle. And Deneb has a magnitude of 1.25, so it's a whole magnitude less bright than Vega, which means it's about 2.5 times fainter. But it's 1,550 light years away. So as soon as you see a kind of a reasonably bright star that's a fairly great distance away, then you know it has to be inherently a very bright star. Well, it turns out that it's 19 solar masses and it's 202 solar radii. So that's basically the curve of Deneb compared to the sun. It's a monster, but interestingly, it's not a red star. It's a blue star. Its surface, the temperature of this enormous star is 8,500 Kelvin, which makes it white. And it's about 1.47 times hotter than the sun. And the lowest estimate of its brightness is that it's 55,000 times brighter than the sun. It's been, they've gone up to closer to 150, I think, thousand times brighter than the sun. That's because of uncertainties as to exactly how far away it is. But minimum 55,000 times brighter than the sun. So Deneb is a monster. It's a huge, heavy star. But interestingly enough, it is not on the main sequence. In other words, it's not burning hydrogen as its main fuel. It's gotten past that. That's why it's bloated up to this enormous size. So it expects a supernova in roughly the next million years. So it's nearing the end of its life. It's actually reduced it was about 23 solar masses, I believe, when it was young, but it's burned off and scattered some of that mass. So it's expected to go to a supernova in the next million years. It's also the tail of Cygnus the Swan. And one of the outstanding features of Cygnus the Swan is that it actually resembles a swan, which is so different from many of the other constellations. So you've got the tail and you've got the wings and then you've got the long neck. And so, hey, that's a swan. So that's another little significant factoid about Deneb. The other thing is, and this is totally news to me, but it's right next door to the North American Nebula. I've always wondered where that was. Well, you just aim your telescope at Deneb, and parked right next to Deneb is the North American Nebula. So Deneb is the bright blue star there. And then there's another less famous nebula, the Pelican Nebula. So it can guide you right to that very sort of famous nebula shape. So that's Deneb. You've got 3 stars on the summer triangle. 2 are kind of very similar, Vega and Altair. And they're both rapidly spinning, and they're both kind of somewhat a little bit larger than the sun and bright blue. And then you have this monster Deneb, which is the fainter of the 3 from our vantage point, but is actually far brighter. Okay, well, that leaves one more star left in the summer sky that's a really bright one, and that's Arcturus, which it turns out is the actually brightest star north of the equator. It's the 3rd brightest overall. It used to be ranked the 4th, but that's before they discovered that Alpha Centauri was 2 stars. And by the time they teased those apart, it turns out that Arcturus kind of sneaks in there as 3rd. It has a magnitude of negative 0.05. So remember, the lower the number, the brighter the star. And so it's very bright indeed. It's 37 light years away. And it's about 1 solar mass. But it turns out it's substantially bigger, although not a monster by any means. It's 25 solar radii. So I don't know if you can see the sun by comparison in the shot there, but it's just it's a modest red giant. Of course, being one solar mass and yet being so much larger, that means it's basically just hot air. It's mostly just kind of distributed gases that have stretched out and bloated out from the center star. And as I was saying, for a red giant, it's actually rather small. Its temperature is 4,300 K, so that gives it its reddish hue. And it's about 0.74 times as hot as the sun. But because of its enormous, or much bigger size, not enormous, but bigger size, it's 170 times brighter. So that means that if we kind of switched places and put the sun, if we were on Arcturus looking back at the sun would be pretty tough to see, actually. It would be a very low, it would be kind of a 5th magnitude star or thereabouts. It turns out they estimated it at 7.1 billion years old. So it's 1.6 times older than the sun, and it's expected to have about the same lifespan. But one interesting fact about it is that it's moving almost directly towards us, not quite, at 122 kilometers per second, which is very unusual for stars in this neighborhood. So it turns out that it's going to get to its closest that it's going to get about 4,000 years from now. So it's kind of like aiming to miss by about 37 light years. And then it's going to keep on going and get fainter and fainter. And it turns out that about 500,000 years ago, it was too faint to see. And so it's actually come into view by speed, by just coming closer and closer to us. So if you sort of set up the sun in the middle of the chart here, and that upper blue bar is 200 light years away, then basically what's happened over the last 500,000 years or so is that the Arcturus has passed from about 200 light years in 500,000 years to 37 light years. Now this is about as close as it's going to be. And then in the next 500,000 years, it's going to do another 200 light years, and it'll be way out there, and it'll pretty much disappear into the darkness of space. So what's the explanation for this odd high speed? Well, it turns out that they believe that it originated in a satellite galaxy that was devoured by the Milky Way a long time ago. So its origins are quite strange. It's not from around here. It came from a long way off. So 4 stars, easily visible in the summer sky. Something to think about each one. Each one has their own kind of special contribution, either to the science of astronomy or just to the awesomeness of all the things that are up there. Whether it's the rapidly moving Arcturus, reddish, or Vega, which is bright and hot, or Altair, which is kind of like a twin, but it's been the first to be mapped, or Deneb, which is this blue monster way off in the 1,500 light years away. Okay, so that deals with 4 of the 5 brightest stars in the summer. But the 5th one is actually the brightest of all, and that, of course, is the sun. And there's lots of things to say about the sun, and as Charles pointed out earlier, we probably spend more of our time, certainly at events, doing solar observing than anything else. And in the summer, that's a great thing to do because we see a lot of the sun. But I always like to talk about the solstices and the equinoxes. So the summer solstice is at hand. Of course, that means it's the winter solstice for Australia. And I've been studying a bit more this week. And at the solstice, the sun has moved exactly 90 degrees along the ecliptic since the spring equinox. That wasn't clear to me at first, but I now believe that. It's 90 degrees exactly, despite the elliptical orbit of the Earth. It's moved 90 degrees along the ecliptic since the spring equinox. So that means its celestial longitude is 90 degrees. Why that? Well, because 0 degrees is defined by the spring equinox. That's your 0 point. And that also means that the right ascension is 6 hours. And that's due to the annoying fact that astronomers decided to use degrees north and south, but instead of degrees east and west in the sky, they used hours. So 90 degrees of a 360-degree circle is like 1/4 of a 24-hour cycle, which is your 6 hours. So the right ascension of the sun at the solstice must be 6 hours. But you have to be careful. You have to be careful in a number of ways. This is what I discovered this week. The exact position of the sun appears slightly different from different points on the Earth. And so I was looking at it from Seashelt, and it wasn't matching up. It wasn't working up when I was looking at it at using Stellarium, and then later when I used Carte du Ciel, which has been extolled for its accuracy. I also discovered that there's a difference between geocentric and topographic right ascension and declination. So yeah, it depends on whether you're at the center of the Earth or on the surface of the Earth as to what the right ascension and the declination will be. So I mucked around for a long time, and finally I got it all figured out. So the summer solstice this year is at 8:32:08 Pacific Daylight Time. So it's going to be 8:32 and 8 more seconds past that. So this is the first time I've gotten closer than 1 minute. Pacific Daylight Time. So my first question is, will the sun be visible to us at the instant of the summer solstice, when the sun reaches its most northerly point? So you can unmute yourself if you have a contribution, a guess, or a reason to saying yes or no. Will the sun be
that 0832 or 2032 AM?
Oh, I'm sorry. I beg your pardon. Yes, this is 8:32 p.m. I'm sorry. I was caught up in the PDT that I forgot. Yes, p.m. So this is 8:32 p.m. So what would you think?
2032 hours.
Sorry, I'm
2032 hours.
yes,
Yeah,
2032.
The sun sets about an hour later, I believe.
Okay, I think that's a pretty good reason. So that tells me that that we will probably be able to see it. We should be able to see it as long as it's not cloudy. Okay, where will it be in our sky? Someone else. Where will it be in our sky?
West. Go west.
That sounds
Northwest.
What's that?
Northwest.
Okay, northwest. Okay. Okay, so where will it be directly overhead? This is a question I always ask whenever we're talking about equinoxes and solstices. Where will the sun be directly overhead?
Oh, on the Tropic of Capricorn, or is it Cancer?
Cancer. 23.4 degrees
Okay.
north of the equator.
Okay, so that's okay. That's true, but that's a circle that goes all the way around the Earth. But there's only one actual point along that circle that it will be directly overhead.
Oh, let's see if it's okay. Wait, 8:32 is
Okay, I hear some whirring of. While somebody sounds like
China.
What's that?
China.
China. Okay.
Somewhere around there.
Somewhere around there. What do you? Any disagreement or agreement? Anybody chime in?
India.
6 hours west of here.
Sorry?
India.
6 hours west of Seashell.
Okay, and how did you get 6 hours?
Because if it's going to be noon, summer solstice is 8:32, add 6 out here, it should be there in 6 hours, right? Because it takes 6 hours for the Earth to rotate from 8:32 to noonish. It's a
Well, yeah, I'm not
yeah.
where you're getting the 6 hours.
Well, I just
Okay,
heard
4.5. Pardon me.
4, yeah. Bruce, incidentally, Mike C. Says in the chat, he would definitely be able to see the sun in the sky because he's in the Northwest Territories of Fort Smith.
Okay, right. Okay. Yes. Okay. No, but even in Seashell, we'll be able to see it. We can't always see the solstice or the equinox when it actually occurs, but we can see this one. I'm just, struggling a little bit with the 6 hours. Of course, this is daylight saving. So if we were to make it more normal, it's actually 7:32. But that would seem to me that it's 7.5 hours to the west of us. So anyway, first of all, the latitude will be 23 degrees, 26 minutes, and 14.7 seconds. The longitude will be 127, 24, 41.
127.
Now, to get to that exact one, you have to have, you can't just do a rough calculation because,
Shanghai.
oh, not quite Shanghai. Where are we?
Well, I can see Taiwan.
Yeah, okay, I can see Taiwan too. It's not a very accessible spot, actually, that you can't, the hotel.
Oh, Taiwan is on the Tropic of, whoa.
What's that?
Taiwan
Anyway,
is
so there you go. You've
off
got
of Taiwan. It's going to be off of Taiwan.
Taiwan, you're south of Japan, you're north of the Philippines, kind of in the middle of a very deep part of the ocean, as you can see.
Is it in the Ryukyu Islands?
You got me. I don't know where they are.
Right there.
Just these little guys up here?
Yeah, somewhere.
Yeah. Okay, well. Good.
Maybe, I don't know if that might be north of the Tropic of.
But I think that it would be a little bit difficult.
Oh,
It looks like we're on Guam or the Marianas Islands.
They're south of there.
it looks like it's in a trench.
Yeah,
Which is
yeah,
the Marianas
it's
Trench.
not the deepest one, but it's definitely a trench. Or
It's
near-
in between Taiwan and the south end of Japan, and the Ryukyu Islands are, I believe, up to the north. If you look directly north of that marker, you're seeing, I believe, somewhere in there, or maybe it's just there, Okinawa.
Oh, okay.
Oh, yeah.
Very good. You know more about it than I do then.
2 point.
Anyway, so what this means then is that the sun is just it moves north rapidly at the equinox, and then as it gets farther north, it kind of slows down each day. It's getting slower and slower and slower until finally it comes to a stop. And the instant it comes to a stop, it happens to be right over that point. To the nearest second, that's 8:32 and 8 seconds. And then it starts to trend south again. So that is the solstice. It's coming up. Wait for it. And you will be able to see it.
Well, that's sort of interesting. In a way, my ballpark was about right, because I figured, okay, if I'm in Sechelt and the sun's going to be close to the western horizon, if it was really to be like right bang on, it'd be like somewhere around there somewhere. And like it was in the ballpark.
Yeah, well, who did you say China? Somebody said China.
Yeah,
And
I said China because I was thinking like if
I
you
thought that was good. Yeah, that was a good guess. That was a good guess. That's not bad at all.
just sort of thinking of the angles and the ball, you know.
Right? Yeah, absolutely. Good. Okay. So basically, the executive of the Sunshine Coast Astronomy Club has been talking about the possibility of summer events. Of course, we're waiting on what the public health announcements will be. But we are not, we are kind of hopeful that there might be a summer event or two. So watch for that. The airport construction has led to a different access road to our observatory. We're going to have to go, when we come up to Field Road, we're going to have to turn right, and then we're going to go along a little ways and then turn left, and then we'll go around the north side of the airport, and then again a sharp left, go back and go through a different gate than the one that we're used to. But that'll all come up. We'll give you all kinds of details on that when that gets set up. Right now, they're actually using that road for the construction, and so we can't really open our observatory to the public, even if the public health office was okay with it.
Well, I'm
And
glad it's not around the long way, like around the far end of the runway, like the very far end and back, because that would be
No.
quite a long drive.
no, this is around the short right-hand end, east end.
I think I've been up there.
Okay,
It's by the hydro line, and it's really on the outside of the fence rather than the previous road, which was on the inside of the fence.